Hello everyone, welcome to the lecture session of the module conduction. In the last lecture, we have discussed the unsteady state heat conduction, that is the lumped parameter analysis, and there we have got two dimensionless terms, that is Fourier number and Biot number, and we have discussed two numericals based on the equations of the lumped parameter analysis. Today we will be continuing that discussion of the unsteady state heat conduction. So let us start today's lecture. So we will continue the solution of different numericals with the equations related to the lumped parameter analysis. So let us read the question first. A 15 millimeter diameter mild steel sphere, the thermal conductivity of which is given 42 watt per meter degree centigrade, is exposed to cooling airflow at 20 degrees centigrade, resulting in the convective coefficient H equals to 120 watt per meter square degree centigrade. Now we need to determine the time required to cool the sphere from 550 degrees centigrade to 90 degrees centigrade. That means we need to calculate the value of the tau. Next, number 2, instantaneous heat transfer rate 2 minutes after the start of cooling. And number 3, total energy transferred from the sphere during the first 2 minutes. So these are the three things that we need to determine in this numerical. So what are the things given here? For mild steel, the density is given 7850 kg per meter cube. C is given 475 joule per kg degree centigrade, and alpha, that is thermal diffusivity, it is given 0.045 meter square per H. So let us start the solution. First we need to find the time required to cool the sphere from 550 degrees centigrade to 90 degrees centigrade. So how to do that? So for that we need to apply the formula of the lumped parameter analysis, but before that we need to first check the value of the Biot number. So the formula of the Biot number, it is HL by K, that L is the characteristic length. Now how, in that formula of the Biot number, it is HL by K, the value of H is given in the question 120 and K is given 42. That means we need to calculate first the value of the characteristic length, that is LC. So how to calculate the value of this characteristics length? So in the last lecture we have discussed the formula to calculate the characteristic length, it is the volume divided by the surface area of that geometrical shape. Now here for this sphere, the characteristic length, it is the ratio of its volume divided by the surface area. So it will be 4 by 3 pi r cube divided by 4 pi r square. So ultimately we are getting r by 3. The value of this r, it is given, that is 7.5 millimeter, that is 0.0075 meter. So ultimately we are getting the value of the characteristic length as 0.0025 meter. So in this way we have calculated the value of the characteristic length first. Now we need to find the value of the Biot number. So the value of the Biot number, it can be calculated using the formula, that is HL by K. So the value of H is given in the question, the value of LC, that is characteristic length, we have just now calculated, and the value of thermal conductivity, that is K, it is also given in the question. So that means we can calculate the value of Biot number, which we are getting as 0.007143. Now since the value of the Biot number, it is less than 0.1, so we can use the lump theory or lumped parameter analysis in this numerical to solve the required values which are given, which we need to calculate. Now how to calculate the value of the Fourier number. The formula to calculate the Fourier number, it is alpha tau by LC square. Now the value of alpha, that is thermal diffusivity, it is actually given in the numerical, that is 0.045, and tau is the time that we need to calculate for the first part of the numerical, and the value of LC, it is the characteristic length which we have calculated just now. So ultimately we are getting the value of the Fourier number as 7200 tau. Now if we apply the formula of the lumped parameter analysis, then the equation of this lumped parameter analysis, it is T minus TA divided by Ti minus Ta. This is equals to e to the power minus Biot number into Fourier number. Now if we put all these values in this equation of the lumped parameter analysis, then we are getting that only the value of tau is remaining except the value of this tau, that is the time. All the other values are given in the question. Now if we put all these values that are given in the question in this lumped parameter analysis equation, then ultimately after 2 or 3 steps we are getting the value of the tau as 0.03937 hour. So that means if we convert this into second, then we are getting the value of the time as 141.7 second. So this is the answer of the first part of this numerical. We have first calculated the value of the characteristic length so that we can find the value of the Biot number. After that we have again calculated the value of the Fourier number so that ultimately we can put the value of the Biot number and Fourier number in the equation of the lumped parameter analysis. And after that, using the equation of the lumped parameter analysis, we have calculated the value of the time. So the next part of this question, it is we need to find the instantaneous heat transfer rate 2 minutes after the start of cooling. So 2 minutes is equals to 0.0333 hour. So to find this instantaneous heat transfer rate, the formula is equals to minus HA into temperature difference into e to the power minus Biot number multiplied by Fourier number. Now if we use this formula, in that case the value of Biot number and Fourier number, it is already known to us. Now here, in case of the Fourier number, the value of Fourier number, we actually got 7200 multiplied by tau. But for the first part of the question, the value of tau we have got as 141.7. But for the second part, we need to calculate the heat transfer rate when the value of tau is given 2 minutes. So that means that value of tau we need to use here to calculate the value of Fourier number. So that means ultimately we are getting the multiplication of Biot number and Fourier number equals to 1.7126. Now if we put this value in this equation, then finally we are getting the value of instantaneous heat transfer rate as minus 8.1 watt. So what is the significance of this negative sign? So this negative sign implies that the heat is given off by the sphere. Now in the next part of this question, we need to calculate the total energy transferred from the sphere during the first 2 minutes. So that means again in the formula of the Fourier equation, we need to use the value of tau as 0.0333 hour. Now for that, the equation that we will be using, this is equals to Q prime, this is equals to rho Vc multiplied by the temperature difference, then multiplied by e to the power minus Biot number into Fourier number minus 1. Now in this equation, all the values are given in this question. So finally we are getting the total energy transferred from the sphere during the first 2 minutes. This is equals to minus 2862.3 joule. So in this way, using the concept of the lumped parameter analysis, and using the equation for the two dimensionless parameter, that is Biot number and Fourier number, we have calculated all the required things in this question. Let us move to the next page. So let us try to solve one more numerical. We will discuss this one. An egg with mean diameter of 40 millimeter and initially at 20 degrees centigrade is placed in a boiling water pan for 4 minutes and found to be boiled to the consumer's taste. For how long should a similar egg for same consumer be boiled when taken from a refrigerator at 5 degrees centigrade? Take the following properties for egg. So what are the things given for the egg? The thermal conductivity, it is given 10 watt per meter degree centigrade. The density rho is given 1200 kg per meter cube. C is given 2 kg per 2 kilojoule per kg degree centigrade, and the convective heat transfer coefficient, it is 100 watt per meter square degree centigrade. Now in this question it is given that we need to use the Lamb theory. So that means it is more clear to us now. There is no more confusion regarding the use of the Lamb theory. Now there is one condition based on which we can use the Lamb parameter analysis. So that is the Biot number value, it should be less than 0.1 in case of this different geometrical shape. So for that we need to first calculate the value of the Biot number. As the formula of the Biot number is HLC by K. Here the value of H and K, these are given in the question. That means we need to calculate the value of the characteristic length. Now the formula for the characteristic length, it is the ratio of the volume divided by the surface area for this given geometrical shape. Now the value of the characteristic length we are getting as R by 3. So that means the value of the Biot number we are getting is 0.067. So that means it is less than 0.1. So that means we can undoubtedly use the Lamb parameter analysis or the Lamb theory. Now the formula or the equation for the Lamb theory, it is T minus Ta divided by Ti minus Ta and e to the power minus Biot number into Fourier number, that is actually e to the power minus Ha by rho Vc multiplied by tau. Now this Ha by rho Vc, this part can be written as H by rho C into A by V. So all the values are given in this question. So you can put all these values here. So that means ultimately we are getting the value of Ha by this is equals to, ultimately we are getting 1,00625. Now if we use this value in the equation of the Lamb parameter analysis, then we are getting that only the value of the T, that is the temperature, it is unknown to us, as all the other values except T is known or given in the questions. That means we can easily calculate the value of T from this equation. That means the value of T we are getting is 82.16 degrees centigrade, which is approximately equals to 82 degrees centigrade. Now we need to find the time, that is tau. So, and when we need to find the tau, we need to find this time when Ti is 5 degrees centigrade, the ambient temperature is 100 degrees centigrade, and the T is 82 degrees centigrade that we have calculated just now. Now if we put all these values of the temperature in the Lamb parameter analysis equation, then ultimately we can calculate the value of the time, that is tau, as 266.13 seconds, that is 4.435 minutes. So using the concept of this Lamb parameter analysis, that is also given in the question, that we need to use the Lamb theory. So based on those equation, the Biot number and Fourier number and the equation of the Lamb parameter analysis, we have calculated the necessary things in this question. Let us discuss one new topic, that is the transient heat conduction in solid with finite conduction and convective resistances. Here the value or the range of the Biot number, it is 0 to 100. Till now, when we have discussed the value of the Biot number, it was less than 0.1 for the given shapes. Now whatever we will discuss right now, here the range of the Biot number, it is 0 to 100 in this range. Now in the given diagram, the transient heat conduction in an infinite plane wall, it is given. So here we need to consider the heating and cooling of a plane wall having a thickness of twice L. So the total thickness of this infinite plane wall, it has been considered as twice L and extending to infinity in y and z direction. Now let us assume that the wall initially is at uniform temperature. So the initial temperature is uniform, has been considered, and both the surfaces x equals to plus minus L are suddenly exposed to and maintained at the ambient or surroundings temperature Ta. Now as this plane wall, it is extended to infinity in y and z direction, so that means the governing differential equation, it will be only in the x direction. It is one dimensional heat conduction equation, so that means del 2t del x2, this is equals to 1 by alpha del t del tau. Now the boundary conditions, it can be considered here at tau, the time equals to 0, t equals to ti, that is the initial temperature, and at x equals to 0, in that case dt dx, this is equals to 0. And the third condition, this is at x equals to plus minus L, when the surfaces of this wall are exposed to the ambient or surroundings temperature. In that case, Ka dt dx, this is equals to Ha T minus Ta. That means the conduction heat transfer equals to the convective heat transfer at the wall surface. Now if we put all these boundary conditions in the governing equation, governing differential equation, then after some rigorous mathematical analysis, we will get the equation 4.13, that is t minus ta divided by ti minus ta. This is equals to the function of x by L, then HL by k and alpha tau by L square. So what are these? So that means what we are getting when the conduction resistance is not negligible. Ultimately here we are getting, or we have considered, the conduction resistance is not negligible. The temperature history becomes a function of Biot number, that is HL by k, the formula is known to us, then alpha tau by L square, this is Fourier number, it is also familiar to us, and the another dimensionless parameter, that is x by L, so which indicates that the location of point within the plate where temperature is to be obtained. So the dimensionless parameter x by L, it is replaced by small r by capital R in case of cylinder and sphere. So this is the equation or the concept we are getting in case of a infinite plane wall and cylinder and a sphere, that the temperature history, it becomes a function of Biot number, Fourier number, and a dimensionless parameter, that is x by L. Let us move to the next page. So from the equation 4.13 in the earlier page, graphical charts have been prepared in a variety of form. So what are those graphical charts? These are actually known as the Heisler charts. So these Heisler charts, it depicts the dimensionless temperature, it is To minus Ta divided by Ti minus Ta, it versus the Fourier number for various values of 1 by Biot number for solids of different geometrical shapes such as plates, cylinders, and spheres. So that means, what is this Heisler chart? This Heisler chart, it depicts the dimensionless temperature versus the Fourier number for various values of 1 by Biot number for different geometrical shaped solids such as plate, cylinder, and sphere. So this is the Heisler chart in case of the infinite plate of thickness twice L. So in the x-axis we can see it is the Fourier number, and in the y-axis we can see it is the temperature history, or the theta naught by theta I. And here in the middle you can see that one thing is written k by hl, so it is actually 1 by Biot number, as Biot number is hl by k. So here the opposite of Biot number, 1 by Biot number, that is k by hl, is given. So this is the Heisler chart in case of an infinite plate. Next, this is the Heisler chart in case of the cylinder, infinite cylinder. And next, this is the Heisler chart in case of the sphere. So these charts will be very much useful to us when we will solve different numericals. So these charts provide the temperature history of the solid at its mid planes, that is when x equals to 0. Temperature at other locations are worked out by multiplying the mid plane temperature by correction factors. So how to do that? In that case, okay, first let us go to those charts. So this is the chart when the temperature is a function of center temperature in an infinite plane of thickness twice L. So in this value, when in this chart can be used when x is not equals to 0, and the values of x by L, it is given from 0.2 to 1. So similar type of chart is there in case of an cylinder and in case of a sphere. So again, all these 6 different charts regarding the Heisler chart will be useful to us, and we will use all these charts while solving the different numericals. Now, for this correction factor, the following relationship which is given here, theta by theta I, this is equals to t minus ta divided by ti minus ta. This one will be represented in some other form, that is t naught minus ta divided by ti minus ta multiplied by t minus ta divided by t naught minus ta. So this relationship will be used when the mid-plane temperature by correction factors will be required when the x is not equals to 0. That means the temperature at other locations we need to find. Now the values of the Biot number and Fourier number are used in the Heisler charts. These are evaluated on the basis of a characteristic parameter S, which is the semi-thickness in case of plates and the surface radius in case of cylinder and spheres. Now when both conduction and convection resistances are almost of equal importance, the Heisler charts are extensively used to determine the temperature distribution. So these were some basic concept regarding the Heisler chart and its related equations. Now based on this concept and the equations, and based on these Heisler charts, let us try to discuss some numerical and how to use this Heisler chart. Let us move to the next page where one numerical is given. Let us read the question first. A 60 millimeter thick large steel plate. Now for this large steel plate, the thermal conductivity and thermal diffusivity both are given. And initially, that means the initial temperature, initially at 440 degrees centigrade, is suddenly exposed on both sides to an environment with convective heat transfer coefficient 235 watt per meter degree centigrade and temperature 50 degrees centigrade. Now we need to determine the center line temperature and temperature inside the plate 15 millimeter from the mid plane after 4.3 minutes. So that means the value of tau is given here 4.3 minutes. So first we need to find the temperature at the mid plane or the center line of the plate T0. Now first we need to find the characteristic length for this steel plate. So that is LC equals to 60 by T. So this is equals to 0.03 meter. Now the Fourier number can be calculated using the formula that is alpha tau by LC square. So in this case, the alpha, that is the thermal diffusivity, it is given in the question 0.043. The value of tau, that is the time, it is given 4.3 minutes. And LC, that is the characteristic length, we have calculated just now, that is 0.03 meter. So putting all these values in the equation of the Fourier number, in the formula of the Fourier number, we have calculated its value as 3.424. Now to calculate the Biot number, we need to use the formula that is HLC by K. As all the values are known to us, we can easily calculate the value of Biot number, that is 0.165. Now here, as the value of Biot number is greater than 0.1, then the internal temperature gradients are not small. Therefore, the internal resistance cannot be neglected. Earlier, when the value of the Biot number was less than 0.1, in that case, we have neglected the internal resistances compared to the surface resistances. So in that case, we have used those lumped parameter analysis approach. Now here, as the Biot number is greater than 0.1, then in that case, the internal resistances can't be neglected. So that means the plate cannot be considered as a lumped system. Now as the value of Biot number is less than 100, so the Heisler charts can be used here in this numerical to find the solution of the problem. Now how to use the Heisler chart? So in the Heisler chart, the different values that were given, that is theta by theta naught, that is versus the Fourier number with respect to, and those values were given for 1 by Biot number. Now the Fourier number we have calculated here 3.424. 1 by Biot number, it is also known to us, that is 6.06, and at the mid plane x by L, this is equals to 0. Now from the Heisler chart, we need to calculate that temperature function, that is theta by theta naught by theta I. So if Fourier number is 3.424, the 1 by Biot number is 6.06, and x by L, this is equals to 0. So let us go to the Heisler chart in case of an plate of thickness twice L. Now if we look in this chart closely, the Fourier number, it is given 3.424. So from the first 0, 1, 2, 3 in the x-axis, the Fourier number, it is 3.424. So that means almost 3.5. So it will be in between 3 to 4. And the 1 by Biot number, that is K by HL, it was given 6.06. Now if we look closely at the middle of this chart, then we will get the value of this 1 by Biot number at 4, 5, 6, 7. So corresponding to the line of this Biot number 6, when it will meet the Fourier number 3.4. So in that case, we need to find in the y-axis, first we need to find the intersection point of the Fourier number 3.4 and the Biot number, 1 by Biot number is 6.06. And the intersection point of these two different lines we need to find from this Heisler chart. Now corresponding to that intersection point, we need to find the value of the theta naught by theta I from the y-axis value. So based on this, we have identified the value of theta naught by theta I from this Heisler chart. So this value we are getting almost 0.6. So if we put this value here, So we can find the value of the T naught from this equation. So we are getting the equation of the T naught as 284 degrees centigrade. Now we need to find the temperature inside the plate 15 millimeter from the mid plane. Now in this case x by L, it is not 0. So what is the value of the x by L? It will be 15 divided by 30, that means 0.5. So now we need to use another chart of this Heisler relation when the x by L is not equals to 0. So which chart we will use now when the x by L is given 0.5 and 1 by Biot number is 6.06? So in that case we will use this chart. So x by L is 0.5 and Biot number it was 6.06. Now 1 by Biot number is 6.06, so that means in the x-axis value we can identify the value of the Biot number from, it will be in between 5 to 10. So that point after 5, that will be the line of the Biot number 1 by Biot number when it is 6, and the value of x by L, it is given 0.2, 0.4, 0.6. So in between 0.4 and 0.6 we can assume the x by L value of 0.5 line. So when these two things, these two lines, that is x by L 0.5 and 1 by Biot number is 6, when these two things, we need to find the intersection of these two. If we can easily identify the intersection of these two, x by L and 1 by Biot number, so corresponding to that in the y-axis we can get the value of the temperature function as almost 0.96 or 97. Okay, so corresponding to the intersection point of x by L 0.5 and 1 by Biot number 6.06, we are getting T minus TA divided by Ti minus TA. This is equals to 0.97. So this thing we are getting from the Heisler chart, that is the position correction factor. So if we use this value from the Heisler chart, then ultimately we can calculate the value of the temperature inside the plate from the mid plane, that is as 276.98 degrees centigrade. So using this procedure we can get the value of this different temperature, and I think now we are clear how to use the Heisler chart in case of the plate when the x by L is 0, and for the second part of this numerical we have seen another chart when the x by L it is 0.5. Next, similar type of numerical is also given, but it is for a cylindrical bar. Now in this numerical also, again the characteristic length LC we have calculated, the Biot number it is we have calculated. So the Biot number we have got greater than 0.1, but it is less than 100, so that means we need to use the Heisler chart here. So the Heisler chart for the cylinder we need to use here to calculate the time taken in the surface temperature of the shaft. So in the similar procedure, if we use the Heisler chart, then we can easily calculate all these required things. So I think this numerical is not very complex, only we need to use the Heisler chart for the cylinder. So today we have discussed the continuation for the different numericals of the lumped parameter analysis, and after that the procedure and the concept of the Heisler chart we have discussed today. How to use the Heisler chart, when to use, based on which value of the Biot number we can use the Heisler chart and not the Lamb theory analysis. All these things and all the 6 different Heisler chart we have discussed today. So this is the end for today's lecture.